Section 3 involves what we call the first derivative test. It's not really a test of our knowledge. It's kind of a theorem. So the first derivative test, and there is also a second derivative test that we'll learn in the next section. Basically, the first derivative test helps you find relative extrema, which is what we've been working on so far in this chapter, finding minimums and maximums, minima and maxima. So a review of the things that we need to know, like instantly. If the derivative f prime is greater than 0 everywhere on some interval, I'm not talking about for all time, I'm talking about just over an interval, then that means that the function is increasing over that interval. Because this means that the slope of the function currently is positive. And if the slope is positive, then the function must be like increasing. Okay? At the same time, if the derivative is less than 0 everywhere over an interval, then the slope of the function would be negative, so therefore the function must be decreasing. So we can kind of start to talk about when a function is increasing or decreasing, and then down the road we'll use that information to tell us when we have a maximum or minimum. If the derivative is equal to 0 everywhere on some interval, then the function is constant over that interval. It's not changing. Or think of a horizontal line. The derivative of that function would be just 0 because the slope is 0. So the function is not increasing or decreasing. It's just sitting there. Okay? And at the same time, if f prime equals 0, we could call that what? We've been finding where the derivative is equal to 0. Yeah, that's your critical number. So you could have increasing, you can have decreasing, you can have neither. It's just sitting there constantly. Or that could actually be a critical number. If your interval was a specific number, then you would have your critical number. So let's take a look at the graph here. From here out to here, so all of this stuff going that way, the function is doing what? The function's increasing. You read a function from left to right. So we're increasing in this region. Then we hit a critical number. We hit looks like a maximum there, a relative maximum at that ordered pair. Our critical number would be right here. Then we turn around and start decreasing. So from here to looks like about our next critical number, which appears to be right about there. We're decreasing. I'm just going to abbreviate because I can't fit decreasing in there. And then we turn back around, and from here on, we're increasing. So we have 3 intervals here. What are our intervals separated by? Critical numbers. So what we're going to do is we're going to find critical numbers, and then we're going to set up intervals. We'll have 3 intervals, because technically we won't have this graph necessarily. And then we'll have to do some sort of test to figure out, it's not the first derivative test, but we'll have to do some sort of test to figure out if the function is decreasing or increasing over that interval. And that will help us form a picture in our minds of what the graph is doing without actually graphing it. By the end of this chapter, you're going to be able to graph functions without actually using some sort of graphing utility. You'll be able to graph them by hand. And this is the first step of graphing functions.
Are we going to be using interval?
Yeah, so you'll be using interval notation. We'll start off writing just like words down, and then quickly we'll jump to interval notation. The book likes to use interval notation, and so do I, because it's a lot simpler to use as long as you know how to read it. So we will be doing that pretty much on the next page. All right, so just starting with a very basic function. We have the graph sitting in front of us. We can see that it has an increasing period, and then it turns around and starts decreasing, and then it increases again. So obviously, we're going to have some situations here that we're going to have to talk about. But we want to do this algebraically. So find the intervals on which the function is increasing or decreasing. Find your critical numbers first. So that means I need to take the derivative, f prime of x equals 6x squared minus 6x. That's it. Okay, to find critical numbers, what do we do? Set that equal to 0. And then can factor out 6x, and I'm left with x minus 1 equals 0. Zero product property, 6x equals 0, x minus 1 equals 0. So x equals 0, x equals 1. Those are your critical numbers. That's where you are going to have a slope of 0. And if you look at the graph, here's 0 right here. We do have a slope of 0. Here's 1 right here. We do have a slope of 0 there. All right, so it looks like we're doing pretty good so far. Now what we want to do is set up intervals. So I'm going to set up a table kind of like I did in previous sections where we have the interval my interval will be negative infinity to my first critical number, which is 0. And I'm kind of leaving space underneath. You'll see why here in a second. My next interval will be 0 to 1. And my last interval will be 1 to what? Positive infinity. Now I'm not including 1 or 0 because those are my critical numbers. I already know that the function is doing nothing there. It has a slope of 0. So I'm not going to include them. What I'm going to do underneath what I just wrote is use interval notation. And then from here on out, we'll just use interval notation. So how do I write negative infinity to 0? I'm not including 0 in interval notation. Parentheses, negative infinity, comma 0. So I could read that as negative infinity to 0. And the parentheses are telling me I'm not including either of those. Here, so 0 to 1, and I'm not including either of those. I'm not including critical numbers. And finally here, so 1 comma infinity, you read it as 1 to infinity, and they're all parentheses. So for interval notation on these, you'll use parentheses. You're not including critical numbers. No. Nope. Nope. Don't need it. This is my interval here. This is my interval here. This is my interval here. I don't have to represent union or intersection or anything like that. I'm just saying this is my interval. Okay? So, and I don't even have to write the word interval over here. I'm just doing that to show you that that's what we're doing. All right? So now after we get our intervals down, we're going to put down a test number. The test number is going to be in the interval. So just pick a number that's easy within the interval, from negative infinity to 0. Negative 1, yeah, go with the easiest number you can think of in that interval. Now 0 to 1, a little tougher. So 1/2, use fractions. And then 1 to infinity, how about 2? Those numbers are going to give me a sign. I don't care about the value of the number that they give me. All I care about is the sign. I'm going to take these numbers and substitute them into f prime of x. They will give me a sign, and the sign that they give me will tell me what the slope is there, positive or negative. And if the slope there is positive, then over the entire interval, it is increasing. If it's negative, then over the entire interval, it's decreasing. Make sense? Okay. So now, again, we don't care about the number, we just care about the sign. And I'm going into the derivative. So I take negative 1, and I substitute it into the derivative, which is sitting right here. Negative 1 squared is positive, so I have positive 6 here. And then negative 6 times negative 1 is positive. I'm going to wind up positive. That means I'm increasing over that interval. So I'm going to write increasing. Then over this interval, we have 1/2. So I substitute 1/2 in, and I get 1/4 here. This is 6/4. It's positive. Here I get negative 6 times 1/2, which would be negative 3. So I have a positive 6/4 minus 3. I think the minus 3 wins, right? So we wind up negative. we are decreasing over this interval. Finally, we take the 2, plug it in. 2 squared is 4, so we have 24 here minus 12 here. We wind up positive here, we're increasing again. So now to wrap up the problem, it says find the intervals on which this function is increasing or decreasing. Well, we found out that we are increasing on the interval from negative infinity to 0. And we're also increasing on the interval 1 to infinity. And now you can use your union or intersection. And then we're decreasing on the interval 0, 1 only. So this is the answer we're looking for here. So it seems like it's probably a good time for some important safety tips for finding intervals on which a function is increasing or decreasing. The first thing you want to do is locate all your critical numbers. And the critical numbers, remember, occur when the function is discontinuous or the derivative is equal to 0. So look for discontinuities like division by 0. Then look for your derivative and set it equal to 0. Then use your critical numbers to set up your intervals like we just did. You can use your interval notation there. Then pick test values that are in the intervals that you just set up to determine the sign of f prime. This is very important. A lot of times people will get confused and they'll go into f instead of f prime. You have to go into the derivative because you're trying to figure out what the sign of the slope is. The sign of the slope tells you whether or not you're increasing or decreasing. Then use your knowledge of the sign of the derivative, which is what I just said, to determine whether the function is increasing or decreasing, and write it down. And then I would tack on to the end, organize your answer in a way that is easy to find, like I just did on that last problem. A couple of special circumstances. Sometimes a function can be always increasing or always decreasing. These are examples of both. The one on the left, the function is x cubed, and it's always increasing. We do go horizontal here, so there would be a critical number there. But when you set up your intervals from negative infinity to 0, and then from 0 to positive infinity, your test points might be negative 1 and positive 1. You would find increasing here and increasing here. So the function is just always increasing. It does have a critical number, it's just always increasing. On this one, we have a critical number at 0 again, because we have a vertical asymptote. So you'd have the same setup here for your intervals, negative infinity to 0, and then 0 to positive infinity. You'd probably pick negative 1 and positive 1, except this time you'd wind up negative for this side and negative for this side. The function's always decreasing. Now, this one is always increasing, but we're not going to include the critical number when we write our answer. So you would just write always increasing, okay? Or increasing over this interval, increasing over this interval. And technically it would not be increasing here. So the answer in the back of the book would probably be two separate things like we have right here with a union, okay? This one, the function isn't even continuous there. So I would say with certainty that this one would have negative infinity to 0, union 0 to positive infinity, and then it will say decreasing over both of those intervals. All right? This one, because the function is continuous, I wouldn't be surprised if you just saw that. Okay? And it would just say increasing over that interval. But this one, because of the break, it's going to be separate. Now we can talk about the first derivative test. This is the first derivative test right here, that bullet point. At any critical number, if the function switches from increasing to decreasing, you have a relative max. If it switches from decreasing to increasing, you have a relative minimum. If it goes from increasing and stays increasing, then it's neither a max or a min. And the same thing is true for decreasing to decreasing. So I want to put a little sketch on here for all four of these. If I go from increasing to decreasing, so my function is doing something and then it's increasing, and then it switches, there's a critical number, and it goes to decreasing. Do you see how that must be a relative maximum? The same thing is true for decreasing to increasing. Here I'm decreasing, 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 and then if I'm going to switch to increasing, I must kind of turn around. You see how that's a relative minimum? Okay, and then increasing to increasing was like the x cubed function. We're increasing, maybe we'll turn and get to a horizontal tangent there. So that's a critical number, and then we just continue increasing. That's clearly neither a relative minimum or a relative maximum. It's just kind of a wave in the graph. Decreasing to decreasing, same idea. I'm decreasing still. Suddenly I got a critical number, but then I continue decreasing. So that's how that graph would have to look. Neither one of those gives me a relative minimum or a relative maximum. There's an important note here. Unless the endpoint is a critical number, endpoints don't apply here. We're only looking for relative mins and relative maxes. So unless you have an interval of like 0 to 2 and then it wound up that 2 actually was a critical number, you wouldn't consider the endpoints here. Just the critical numbers. So for example, let's find the relative extrema of this function, 1/2 x minus sine x over the interval 0 to 2 pi. Notice now I'm using open interval there. So I'm not going to consider 0 or 2 pi unless I wind up with a critical number at either of those places. So what's the first thing we're going to do? Find the critical numbers by taking the derivative. Actually, since I have the graph sitting here, let's take a look at the graph real quick. We have 0 to 2 pi. There's my interval, okay? So over here, it kind of looks like I might have a critical number there, but I don't care, because it's not on my interval. Looks like I have a critical number somewhere in here, and I have another one somewhere in here. So we're going to find two answers. Normally, if we don't have a graph in front of us, we won't know that, but we know that going into it that we're going to find two. So take the derivative. F prime of x equals what? 1/2 minus cosine x. Okay? Now what do we do? Set it equal to 0 and solve for x. So I'm going to add cosine x to both sides. 1/2 equals cosine x. So we're asking what x values give me a 1/2 when I'm working with cosine. X equals pi over 3 is one of them. 5 pi over 3? Okay. It's nice to have a unit circle. So here's my critical numbers. So now I need to set up my intervals. What will my intervals be? Good. The left endpoint to my first critical number. Between my critical numbers. 5 pi over 3 to 2 pi. My last critical number to my right endpoint. Okay, so now I set up my table. What do I need to do now? Pick some test numbers. So something between 0 and pi over 3. Pi over 4. Stick with fractions. Stick with pi numbers. It's going to make it a lot easier to work with. And somewhere between pi over 3 and 5 pi over 3? Pi? And then somewhere between 5 pi over 3 and 2 pi. Somewhere between 5 pi over 3 and 2 pi. 11 pi over 6? Okay. 3 pi over 2 is not between. Look at your unit circle and make sure you're picking something between. Okay, so now we have our test numbers. And what are we looking for with those test numbers? We're looking at the sign of the function or the derivative? The derivative. Okay, so we're plugging into, so I can call this test number, and then I'll call this f prime of x, just to make sure that I understand that I'm plugging that into the derivative. All right, so I take pi over 4, which is between 0 and pi over 3, and I substitute it in to my derivative. I have 1/2 minus the cosine of pi over 4. The cosine of pi over 4 is square root of 2 over 2. 1 minus the square root of 2. What's bigger, 1 or the square root of 2? The square root of 2 is bigger, so we wind up negative. Okay, then between pi over 3 and 5 pi over 3, we picked pi. The cosine of pi is -1. 1/2 minus -1 becomes positive. So make sure that you are picking the right number there. It does become positive. Now 11 pi over 6. The cosine of 11 pi over 6 is, okay, and then we have 1/2 minus the square root of 3 over 2. What's bigger, 1 or the square root of 3? So we wind up negative. Okay, so the function is decreasing over this interval. It's increasing over this interval. It's decreasing over this interval. So now what I'm going to do, just to help visualize this, is I'm going to kind of draw a little sketch, okay? Obviously I can just look at the graph over here, but when I do this by hand and I don't have a graph in front of me, I'm just going to try to visualize this. We are decreasing, and then we hit our critical number, and then we're increasing again. That gives me a relative minimum. So this critical number right here is a relative minimum. By the way, this line represents my critical number, which is pi over 3. Okay, now we're increasing, and then we hit my critical number, and then we're decreasing again. So this represents a relative maximum. So my critical number, 5 pi over 3, is actually a relative maximum. The question asks me to find the relative extrema. I know that I have a minimum at pi over 3 and a maximum at 5 pi over 3. So depending on how they want the answers, we have pi over 3 is a relative min, and 5 pi over 3 is a relative max, or at least it yields a relative min and a relative max. But if I need the ordered pairs, then I need to take these numbers and substitute them in to find the actual value of the function, which is probably what they want. So our answers will be ordered pairs. So I take pi over 3 and I substitute it in. For f of pi over 3, I get 1/2 times pi over 3, which would be pi over 6, minus the sine of pi over 3. Sine of pi over 3 is square root of 3 over 2. So that would be like 3 square roots of 3 over 6. So I have pi minus 3 root 3 over 6. Pi minus 3 root 3 over 6. So I have an ordered pair of pi over 3, comma, pi minus 3 root 3 over 6. And that is a relative minimum. Don't give me those dirty looks. F of 5 pi over 3 equals 1/2 of 5 pi over 3 would be 5 pi over 6 minus the sine of 5 pi over 3, which is negative root 3 over 2. So that's actually going to turn plus root 3 over 2. So that's like 3 root 3 over 6. So then my ordered pair, or my y value is going to be 5 pi, so equals 5 pi plus 3 root 3 over 6. So then I have the ordered pair 5 pi over 3, comma, 5 pi plus 3 root 3 over 6. And that is a relative maximum. There's your answer. Not impossible to do. Just pay attention. Yeah, it's not exactly pleasant, but that's what it is. All right, we have this kind of cool looking W graph. How many critical numbers are on this graph?
We don't know what. 1, 2, 3.
There are 3.
Why? I thought you couldn't. I thought, like, what? Okay, what doesn't have any sharp points? Because I know there's something that you can't.
So anytime you have a sharp point, then this is not differentiable. Because remember that taking the derivative is telling me that I can put a tangent line. Like if I want to take the derivative, I can put a tangent line right there to calculate the slope. I can't put a tangent line on a sharp point because I could put that tangent line on there and now it's only touching the graph once. But I could also put that tangent line on there and it's only touching the graph once. Or I could put this tangent line on there, or this one, or this one, or this one. There's an infinite number of tangent lines that I could put at that particular point, which means I can't take the derivative there. It's not differentiable. And if the function is not differentiable, then it is a critical number. So we have 3. 1, 2, and then a third one obviously right there where the function goes horizontal. So find the relative extrema. We are going to have to find 3 critical numbers. Now if you look at the original function, there's no division by 0 involved in that function. And that should be obvious to you because the function appears to be continuous on this graph. There's no vertical asymptotes, there's no holes, it's just a function, okay? But when I take the derivative, this will turn into a break in the function, and so will this. It's usually a good indicator that you're going to have some sort of break in the function when you're working with rational exponents. To the 2/3 power, when we take the derivative of that, will become to the negative 1/3 power. And now I'm going to have x's in the denominator, which means I'm going to have to worry about division by 0 when I take the derivative. Okay? So that's where those other critical numbers are going to come from. So let's get that derivative taken, and then we'll probably have time. We'll have time to do that, and then we'll finish the problem up tomorrow. We'll just get started today. F prime of x equals, how do I take that derivative? Chain rule, or general power rule. So I'm going to write what? 2/3. What's inside stays the same. Decay the exponent by 1. Times the derivative of what's inside, which is 2x. So that is the derivative right there. Now what? Okay, I would simplify this before I set it equal to 0, just so that I can see what's going to happen. So the 2x times the 2/3 becomes 4x over 3. But that 3 is in the denominator, and this negative exponent is also going to send that to the denominator. So I'm going to write 3 times x squared minus 4 to the negative, to the positive 1/3 power now. Get out of there. So there's your derivative. Now we're going to look for critical numbers. Yep, we have a rational expression now in our derivative, so we need to figure out where we're going to have division by 0, and those places will be critical numbers. So, where do we have division by 0? Positive or negative 2? 2 squared is 4, 4 minus 4 is 0. 0 to the 1/3 is 0, 0 times 3 is 0. Negative 2 also because of the squared here. Okay, if you can't find them, then take the whole denominator, 3 times x squared minus 4 to the 1/3 power, and set it equal to 0. You'll simplify that down and get x equals plus or minus 2. Those are critical numbers. We also have one more that we can find by setting the derivative equal to 0. So we set this equal to 0, and then what do? Multiply both sides by the denominator, and the denominator disappears, and I'm left with 4x equals 0. So x equals 0 is my third critical number. Now if I look back at the graph, it does look like plus or minus 2 is going to give me these two guys right here, and then 0 is going to give me that guy right there. Those are the 3 critical numbers that I needed. Okay? what's going to happen next? Okay, what are my intervals? We have some time. So actually, I didn't give you an interval to look at, so it's negative infinity to the first critical number, which is negative 2, and then okay. Those are my intervals. I need some test numbers. Negative 3, negative 1, 1, 3. Now you plug it into the derivative function, that's right. So negative 3 squared is 9, 9 minus 4 is 5. 5 to the 1/3 power gives me a positive number. Times 3 is positive. Negative 3 in the numerator gives me a negative number. Negative divided by positive is negative. Remember, you don't need the number, you need the sign. So keep that in mind. Now the same thing here. We take a negative 1 squared is positive, but 1 minus 4 is negative. The cube root of a negative number is negative. So my denominator here is negative, my numerator is negative, I wind up positive. We take 1 and plug it in, we wind up negative. The numerator is positive, so we are negative. And then here we take a 3 and plug it in, we wind up positive here. So the denominator is positive, the numerator is positive, so we are positive. Oh. Negative to positive, decreasing to increasing. We are increasing to decreasing. We are decreasing to increasing. Okay, so we'll finish this up next time.